Okay, so now we start MPI. Okay, so I am stick to Python right now, and Python has in fact simple syntax compared to MPI syntax in C or C++ or Fortran. Okay, and you are not going to lose time. It's going to be same complexity in terms of execution as well as in terms of writing the code. Well, in fact, it's simpler in Python. Okay. So, MPI is called message passing interface, and this for distributed computer systems or distributed HPC system. You have many nodes. So, I have it in my next slide. So, the reference is this book Jacon, and very good support from MPI-4Py documentation. You can look at the documentation, and I will cover the ones we need. I am not going to cover all sorts of MPI functions. As I said, my friend, that you worry about simple ones. I mean 5 functions, if you master, you are okay, you can do most of your work. But sometimes we need more functions. I may mention it a bit later at the end, but you do not need it for this course for sure. Okay. So, this is a example of a distributed system, right. So, we have 2 nodes, node 0 and node 1, and each node has processes, procs, and this process, all the process share a memory. P0 share their memory in the node, and P1 share memory of its own node. Node 1, sorry, node 1, not P1. Okay. So, how many processes we have? 8 processes. Actually, for historical reason or whatever reason, in earlier times, each CPU had only one process, one core. Okay. So, each CPUs have one process per CPU, but now CPU has more cores. Then what do I do? So, each core is also called a process in the programming language. Okay. So, what I am going to do right now, I will, when I do MPI, I will say each core you can you can assign a process, each core equal to process. This is not the correct way to say it, because a ROM processor has 32 or 64 cores. So, that should be called a processor, and the 64 cores should be called cores, but we are not going to change the syntax of the programming language. So, each core when you run it is also called a process, and right now I am not going to do hybrid programming for these lectures. We will assume that there are 4 cores here and 4 cores here, 8 cores. Okay. So, hybrid programming, just to give you an idea, is possible that we can do OpenMP here, and results are shared by MPI across nodes. Then for MPI there will be only 2 processes, because each node acts like a process, but OpenMP has 4 processes or 4 threads. Okay. But just learn first MPI, where each core is a process, and remember, please remember that this memory. So, each process, in fact, for MPI is going to be dividing the memory. Each process will have its own share of memory, and they cannot be transferred. OpenMP had this very interesting mechanism where memory could be shared. So, I did not need to copy paste here and there, but MPI, this within a node itself, I need to divide the memory. Okay. So, there will be division of memory like that. So, in a laptop, when you run MPI, there is certain memory assigned. Not all your memory will be shared only for this MPI job, maybe like out of 4 GB, half a GB will be assigned for this task. Operating system knows how much you need, and then that will be divided into process. Okay. And nodes are connected by interconnect. So, how the data is transferred? We need to transfer data. Okay. If, for example, local sum, there will be local sum 0, local sum 1, 2, 3, 4, 4, 5, 6, 7. There will be 8 local sums from 0 to 7, and I want the total. Then somebody has to take the responsibility. I am going to add them up, and that requires transfer of data within a node as well as across the nodes. Within a node will be done in a PCI bus. There is a connector. This is a PCI bus. But outside the node, I need to use some switch or some wire. Okay. Earlier, there were computers which were just connected by wires, but now typically there will be a switch. Okay. So, the programming paradigm is called MPI. MPI is message passing interface. So, we need to pass messages from one process to other process, where memory is not shared. And okay. So, just to give you another recap. So, what do I do in MPI parallel programming? I discussed that in the past. So, if you have big data, so think of finite difference, okay, or even Ising system and so on. So, your big data, imagine 2D array, and I divide into 3 processors. Typically, I would say 4, but okay, let us make it 3. So, for finite difference, as I said, this derivatives can be done locally for most of the grid points, but some grid points I cannot. For example, the grid point at the edge. For the central difference, it needs the data in the right processor. Okay. So, what did we do? In fact, I mentioned it in my introductory lecture on finite difference. So, we have each process has slightly more data than what is required. So, this is extra data which comes from this part of the process 1. Okay. So, this has to be transferred, right, and that is done by MPI. This data which is here will be copied here, so that I can do the finite difference vectorized in a vectorized way. I will do in one shot, okay, that array index stuff we do not want to do in a loop and all that. So, there will be index, it will just do it in one shot for the 2D grid. Same thing I need to do for the this part. This data will come from the process 3 or process 2, in fact, by C numbering 0, 1, 2. So, this will copy it here. So, you understand, I mean, we need this kind of data sharing. For Ising spin 2, we need to share data like that. So, MPI we need to send, receive, all that has to be done. For some other algorithms, it is more data, like fast Fourier transform requires big amount of data transfer, but we will discuss it later. Okay. So, this paradigm is also called single program multiple data. This is very critical, please pay attention. So, we have 8 processors in the diagram I showed you, 8 cores or 8 processors or MPI processor. All of them will run the same program, okay, same Python code or same C code, okay, the full code. But it has to be told, okay, what is your rank, what is your roll number, and according to the roll number your data will be assigned to you. Okay. So, that is the key part. So, same program will run and say, well, your data is this, and that has to be part of the program. And if you know how to do this, that is it, nothing, no big deal. So, single program runs on all the processors, divide the work equally among processors. This is another important concept. We assume that all the processors have same computation ability. So, no processor should be loaded more than other processors. It is a democracy. Okay. So, we get equal weight. Okay. Nobody should complain. So, same load, and we need to communicate sometimes. I gave the example of finite difference, some data has to be communicated, and the result is collated by a master processor. So, there are different kind of names. This is still some kind of feudal naming, master and slave, or sometimes a master and worker. So, a worker processor and there is a master processor. It turns out master processor also does all the work, okay, but it does some additional work. So, that is what is going to be here, like summing up of all the local sums will be done by master processor. So, using MPI, so this is a Python package called MPI 4Py. So, you are using Python, so MPI 4Py. For C, this is called OpenMPI, MPI-CH2 or MPI-CH3 now. Okay. So, there are different packages, some are free, some are not free, but Python everything is free, MPI 4Py is free. In your laptop you can install by pip install or conda install. Okay. And you run, by the way, running is not just Python. Okay. So, running is, so this is the part MPI basically when you compile it, well, we will do the compilation part for C. Okay. So, it is compiled along with MPI, okay, and it creates a file which is not executed by G++ or Python, it is executed by MPI exec. So, please remember that you will have MPI exec or sometimes MPI run, they are equivalent. So, MPI exec minus n p, this p is number of processors. Your code should be general code, it should work for 2 processor, 4 processor, 50 processors, as long as your division is done okay. You may say that I will have only 2 power n, like 3 processor, if a data cannot be divided in 3, then you do not use it, but this n should, p should be general given the constraint, it would be 2 power n. Okay. So, 2, 4, 8 like that, but it should work for variable number of processors, then Python and then file name.py. So, normally we used to do this, right, but now we need to give the number of processors in the command line. So, number of processors are not inside the program, okay, number of processor is in the command line. In Colab you can use this pip3 install MPI 4Py, and so this is for testing whether your MPI is installed or not. So, MPI exec, this is for system command. Okay. So, this exclamation mark for system command version, and if you write that, then you will, if you get an answer, then you know that package is installed. Okay. Minus version, right, I mean you know this should work. Okay. So, just a brief introduction about MPI. So, you create a communication world, COM world. Okay. So, we have processors which should be talking with each other. Okay. Nobody can say, well, I do not know talk to you, that will not work. So, there has to be a communicator, and so MPI COM world creates this world, communication world. So, it turns out the COM world is a default communicator, is a keyword. If you like, you can create your own communicator or set of communicators that has more complex syntax. Sometimes we need that, okay. We have programmed with different communicators, but for your course or for this course project, this default communicator will work. Okay. So, here each communicator is all the processes are part of a single communicator, but imagine that I have these guys are one communicator, these guys are another communicator, then we need to create more than one communicator. Okay. But for this course we assume all of them are equal member of the COM world, and so the communicator is a group of processors that can communicate with each other. So, important functions. So, MPI.com, so this is another package, well, a class, this is called class. Okay. So, and within that is a function called get size. So, this will give you the number of processors, okay, within the communicator. Okay. We need that how many processors, and I need to divide the data. So, you can call this function, we do not need to wait for some other numbers, you just get that anytime you can get it. And get rank is a process ID. So, as I said, each processor is running the same program, but then the process says, well, process X says, well, I need to know my ID. So, then it is a mpi.com dot get rank. So, it will get its own ID, and this one we do not need it, com self is self ID. Well, this is also one word which is used, but we do not need it for our course. So, this is an example, simple example, hello world. So, please pay attention to this part. Okay. So, this will be common, some part will be common everywhere in all the codes. So, we import first this MPI 4 pi is imported as MPI. I normally use that syntax. It is easy to write MPI, okay, rather than MPI 4 pi long. So, com is we instantiate the class, if you know this object oriented language. So, we create a com mpi.com world. So, the name of the communicator is com, COMM, and com.get rank will give me the rank, that rank means ID, okay. And nprox is a variable which is coming from get size, which is telling us how many processes are in the communicator. Okay. So, remember each process is running. So, I want to see the number of processors, print them. So, obvious mistake I also make now also. So, I can say print number of procs, this one, you just say print, right. So, how many copies will be printed on the screen? Each guy will print, right. I mean, let us say 4 processors. So, and this is same information, number of procs is 4. So, say print. So, this will print number of procs 4, but there will be 4 times it will be printed by 0, process 1, process 2, process 3. By the way, rank starts from 0 to numproc minus 1. These are the ranks. Roll number always start from 0. So, I will print 4 of them, but I want only one information, right. I mean, why should I print 4 of them? So, that is why I put if rank equal to 0, rank equal to 0 is also master process. And 1 onward is worker process, we call them worker process. Okay. And so, this will print only once if I put this if statement. Clear? Is it clear or not? But then as I said, this program will run by all the processors, full program. Unlike multi-threading, where only the function was run by different threads. There is only one program for one process, right, except the function. And then last line is print hello from process rank. So, what will it do? Will it print only 0 or something else? Yeah. So, each process will give its attendance. Okay. So, hello from the 0 guy will say hello from rank 0, hello from process 1 by 1. So, all of them will give attendance here. Okay. So, when I run it by mp exec minus n4 python send receive dot py. So, this is name of the, well, this was I am sure is hello world or something. Okay. So, this the name is, do not worry about it, this is the name of this file. So, remember this is mp exec is the first one, this is a command, this is the executable. We okay. So, it's a dot out is, yeah, that is executable, okay, mp exec, which will take the file name and execute. So, minus n4 number of processors 4 and python and this. So, as expected, as I told you, number of procs is 4 is printed by master node only, and this is the attendance. And why is it coming as 0, 3, 1, 2? Why doesn't it come as 0, 1, 2, 3, 4? As 0, 0, 1, 2, 3. So, all of them are running independently. So, this is one line code only, you know. So, anybody can finish early. So, first time 0 prints, well, I mean, whoever gets hold of the monitor will print it. Then next was 3, last worker prints it, done. So, it goes on like this. In C++, we have called MPI close and so on, but here we do not need closing, it will be done automatically once this program is executed.